Thank you for the introduction, and I'd like to, first thank Rak-Kyeong for, having me here and organizing this very nice workshop. I've been enjoying the talks and beautiful campus very much so far. Before starting, talking about this topic, let me briefly introduce who I am. Okay. So I got my PhD, in 2014 in Tokyo, and I spent about 4 years in the US. And after that, I spent nearly 5 years, in South Korea. And at that time, I was working at the Asia Pacific Center for Theoretical Physics, located in Pohang, which is not far from here. And then currently, from this April, I'm working at the University of Tsukuba in Japan. And my sort of original physics background is in nuclear physics. And after that, I sort of gradually lowered the energy scale of my research topic and started to work on more general, so non-equilibrium physics. Or while I was in South Korea, I started to work on topics on the systems biology as well. And one of the focus of research in the recent few years is the intersection of machine learning and physics. The relation of these concepts can sort of go two ways. So, for example, we can use the machine learning techniques to understand the physical phenomena, or they can be the other way. So we can also use physics techniques or physics concepts to understand the behavior of machine learning models as well. So for example, this topic on diffusion models and path integral, which was presented by Akinori Tanaka on the first day of the workshop, is in the latter direction, and there are some works in this direction. But today's topic, which is about finding self-similarity from data using neural networks, is the former direction. So we are going to use neural networks to extract some physical information based on some experimental data. And in the rest of this talk, I'm going to first give an introduction to this topic, and I'm going to explain the motivation of this present work. And then I'm going to detail on the concepts such as self-similarity or scale transformation symmetry and so-called dead collapse. And finally, I'll be talking about how to sort of detect a self-similar nature using neural networks. So let me start with some introduction. So the self-similarity is a kind of familiar concepts for physicists, and it appears in various places in physical phenomena. In particular, self-similarity arises in the description of critical phenomena in equilibrium physics, and moreover, it also appears in a variety of non-equilibrium phenomena as well. So, and typically, if there's some self-similar solution, it is going to take a form like this, where in the argument, a certain combination of variables appears, and one way to sort of very nicely visualize the self-similar feature is the so-called data collapse. Where we have a number of solutions here, but once we choose the right combination of variables for the axis, all the lines converges to a single line. So that this sort of phenomena is called the data collapse. Let me give you a very simple example, a simple and elementary example to see this feature. So what we consider here is the one-dimensional diffusion equation with this initial condition. So there's going to be a pile of charge at the center at t equals 0. And as you can expect, the system that these charges are going to diffuse towards, outward, in the course of time, in this way. And in this problem, there are 3 units. So we have units of mass and length and time, and so-called physical parameters to describe this system given by those quantities. So we're going to have the total charge Q, which appears in the initial condition. And we also have this mass density and diffusion constant and X and T. So note that when we say, physical parameters, we also, we include those parameters characterizing a system, and we also, include coordinates like X and T as well. So, and those are the, dimensions of each variables. And out of these 5 physical parameters in the system, we can, combine them and make a certain combination of dimensionless variables. For example, we can, combine them into pi1 and pi2. And the number of these dimensions is variable is going to be given by the number of original variables minus the number of units. And indeed, those physical parameters satisfy this relation, as you can expect. And this physical relation can be expressed in terms of the relation between the dimensionless parameters in this way. And because of this fact, we have some, scale transformation symmetries, and by which some certain solutions can be connected, and which is the origin of the self-similarity. So, for example, we can scale those, physical parameters according to the dimensions of the time or length or m. So, for example, this diffusion constant has an inverse dimension in time, and this time has a one dimension of time. So we can sort of rescale these physical parameters, according to these dimensions, and we can perform similar, transformations for length and mass as well. And under these transformations, the solutions remains to be a solution of the system, obviously, because the physical relation is given by the relation of dimensionless parameters in this way, and this is invariant under the transformation given here, obviously, and we can obtain the data collapse by plotting the solutions in terms of the dimensionless variables like pi1 and pi2. So this is one example of self-similarity or data collapse, but it is a rather trivial example of self-similarity. So this type of self-similarity given by the scale transformation according to the units of those quantity is called the self-similarity of the first kind, and it always exists in any physical system, and they can be identified by performing the dimensional analysis. And the fact that it always exists is ensured by the so-called Buckingham pi theorem. But in addition, there can be sort of more non-trivial self-similarity in certain physical systems. And this self-similarity is called the self-similarity of the second kind. And this involves the symmetry and the scale transformation of dimensionless parameters. So this cannot be found by the dimensionless analysis, and it indeed reflects the non-trivial law of the physics inherent in this physical system. So the motivation of the present talk is as follows. So for given experimental data, how can we find the scale transformation symmetries that are non-trivial and the associated self-similar solutions? So conventionally, if you make some model, then I mean, you can sort of, find the physical relation, but I mean, assuming a model introduces some bias. So we want to find the self-similarity or the underlying scale transformation symmetry, I mean, in a model independent manner. So that is the motivation of the present work. So then let me move on to the, next, section. And I'm going to, detail, more on the ideas such as self-similarity or scale transformation symmetry or the associated data collapse. More, sure, sure. This one, right? So the self-similarity of the first kinds are self-similarity, generated by the scale transformation of units. And uh, this one, I want to, I mean, give more detail on this, but in short, it is associated with the, non-trivial transformation of the dimensionless parameters. I mean, so so that is why it cannot be found by the dimensional analysis. Yeah. Sure.
Is there any some typical meaning of the first kind of the self-similarity? So what is the meaning of the first kind of self-similarity? So some kind of case.
Yeah, I think you could say so. It's associated with the arbitrariness of the choice of units. You can use meter or centimeter, and that doesn't change the physical content, but it might change appearance of the solution. So I think you can say that, yeah. Now that you pointed out, I do feel like this is the gauge symmetry of its original sense. It corresponds to the choice of the units. Yeah.
So another thing, is there any some rule to distinguish from the first those?
Yes. So I'm going to talk about that. So let us continue. So we'll consider a certain physical system, and let's say that the eyes are the set of physical parameters to characterize the system. So this Z, so the physical set is going to be specified by a choice of the set of Z, and it takes the value in certain state space, and not but among the points in the state space, not every point can be realized. Under the physical conditions. There's some non-trivial. We are going to assume that there's going to be some non-trivial physics law, which can be explained, which is expressed in terms of explained as NF equations. So we can consider states that satisfy those physical conditions, and we can consider the space of physical solutions to be the set of states satisfying these constraints. And physical system can often have symmetries. We are going to consider the transformation of a certain solution to another solution. And the set of such transformations is going to form a group. So for some choice of an element of this group, we can sort of transform one state to another state like this. And since it is a transformation inside the solution space, it is going to preserve this physical relation, meaning that if this is a solution, then G dot Z is also a solution. And this group is G is called the symmetry group of the system. And among various kinds of symmetries, we are going to particularly here consider a scale transformation, under which each component of Z sub I is going to be multiplied by a factor, that is, positive. Okay? And let's, denote the, group of all the scale transformation asymmetries to be G superscript S, which is the subgroup of this whole group G. And then we can sort of introduce the scale transformations associated with these, self-similarity of the first kind. So in this physical system, let us choose a set of units. For example, we can take mass and kilogram, meters and kilogram and second as a unit to describe the system, for example. And let us denote the physical unit of quantity, physical parameter Zi to be unit sub I. And suppose we consider the rescaling of those units. So let's start with an example. So suppose we rescale each unit by a certain factor like this. Then, the unit of this certain physical quantities, for example, acceleration, is going to be changed accordingly. So the unit of acceleration is going to be made up by square seconds. And under this rescaling of units, it is multiplied by this factor. And we're going to define this quantity as a dimension function of this particular physical parameter. Okay. So as you can see, it just reflects the dimension, physical dimension of this physical parameter. And we're going to define this scale transformation of units, which is the scale transformation of states using the dimension function. So we're going to just scale each physical parameters accordingly to the dimension of those parameters. And we can see that this scale transformation of unit is always symmetry. So this, if we denote the all the scale transformation of the units by G sub unit, it is always in the subgroup of the whole symmetry group. And this fact is ensured by the so-called Buckingham's pi theorem, which states that suppose we have some physical relation like this, it can be always expressed in the form like this, where those pi's are the dimensionless parameters obtained by taking certain products of certain products of the original variables, and the number of those parameters are going to be given by the number of original variables minus the number of units. So since the physical relations are expressed in this way, using the dimensionless parameters, and since dimensionless parameters are invariant under this scale transformations, so we can say that this is always a symmetry of the system, or rather a trivial symmetry. However, there can be, more, non-trivial, scale transformations. So let's denote the group of all the scale transformations, in the system by G superscript S. So G subunit is always a subgroup of this group. And as I said earlier, the self-similar solutions generated by the scale transformation of unit is referred to as the self-similarity of the first kind. And if we have some non-trivial so if this these two groups are equal, then there's no non-trivial scale transformation. But if this group is non-trivial, we have some physical self-similarity, and the self-similarity generated by this group is going to be called as the self-similarity of the second kind. And in the presence of, non-trivial, G sub second group, we can sort of further, reduce, parameters to fewer numbers. But by using the action of these groups, we can sort of, create, the invariant, combinations, that I'm going to denote by a capital Z sub I, which is given by the product of this, dimensionless variables. And the physics law or physical relations, can be, expressed as a relation between those, reduced number of, physical parameters. So, and summarizing, this discussion so far. So originally we have the system, and that takes value in a certain solution space, but we can, reduce the, a solution space, by using the, dimensionless, parameters as coordinate. So, and this solution space is obtained by, taking quotient of the solution space by the action of this, group of the symmetry, scale transformation of the units. And in the presence of, non-trivial scale transformation symmetry, we can further, reduce the state space where the coordinate is given by those, capital Z parameters. And the, action of obtaining this, reduced state space, starting from the original solution space, is called the data collapse. And in the following, we're going to try to find this group, which reflects the non-trivial, scale transformation symmetry from some experimental data. Okay, that is the end of the second part of this talk. So finally, let's talk about, how we can sort of detect self-similar feature from some data. So let me first explain the basic, idea, behind the present method. So we wanted to first note that invariants under scale transformations are always given by monomials, like this form. So it is going to be the invariants under scale transformations are always going to be given by the product of certain power of physical parameters like this. And then for concreteness, let us for example consider a system with the following physical relation. So now the pi i's are already dimensionless parameters, and a certain product of pi's are going to be given by a function of another product of the dimensionless variables. And the scale transformation acts on these pi variables in this way. And we can easily see that if we take this vector c from the orthogonal complement of the vector space spanned by p's and q, then it is going to be to preserve this physical relation. Because for example, if we take this combination, it is transformed under this scale transformation in this way, and we're going to have this factor here. So if c is orthogonal to this p vector, this combination remains invariant. So if we take the c vector from this space, it preserves the physical relations, meaning that it is a scale transformation symmetry. And this structure becomes more apparent, if we introduce the log of the original variable like this, and then the physical relation that appeared in the previous slide can be equivalently written in this way. And so in this notation, I mean, the scalar transformation acts as just a shift of these vectors. Okay. And here, so the problem is, that we want to sort of, so as I said earlier, the the scale transformation symmetry is going to be, specified by the choice of those vectors P and Q. So once we identify these, vectors, we know the scale transformation symmetry, in this system. So, for that purpose, we're going to, approximate or use, we're going to, bring a neural network to sort of approximate the right-hand side of this equation. And we also have, the data, from experiment or from some simulations. So we have a, pair of this, X vector and data corresponding to the left-hand side. So we see here, assume that one combination Q is known, and we want to sort of identify the vector P. Then once we have, this set of data and have a neural network and optimize this neural network, so that, these, two are equal, then we shall be able to, we shall be able to extract the value of P by looking at the values, of the fitted parameters in a neural network. So so for that purpose, the neural network is, sort of structured this way. So it is first combine the variables into as a linear combination, and then there's going to be some generic function. So it is a, very simple idea. And let us, try to use, test this idea, for some, actual experiment. So one of the collaborator is a soft matter experimentalist, and he has done this experiment. So there's a mat, and that is, viscoelastic. So, and he's going to drop a ball into this mat, and he's going to sort of measure the maximum, deformation of this mat. And this is sort of the non-triviality of this phenomena resides in the fact that, so this is a viscoelasticity, and whether it looks, elastic or viscous, depends on the energy scale or the, speed or mass of this ball. So there's going to be some non-trivial sort of regime change of, viscous regime and elastic regime, depending on the parameters. And the set of physical parameters are given by these. So there are 7 physical parameters. And out of those 7 parameters, we can make, 4 dimensionless variables like this. And if we assume a certain sort of physical model, we can show that, these, dimensionless variables are going to satisfy, this relation. And here we can see that certain combinations, appear, certain combinations of those dimensionless variables appear in the argument, meaning that, there are some non-trivial, scale transformation symmetry. So if we, perform the scale transformation that, doesn't change these combinations, then, they're going to create a new physical solution. So, which means that, from the notation from of this slide, we're going to take the Q to be, of this vector, which corresponds to this combination. And our sort of problem is to estimate the correct, P vector, which corresponds to this combination, for given some data. So we first, tested, this method, using, generated simulated data, that sort of obviously, satisfies this relation. We generated 1,000 training data, and the ground truth of this P vector is this one. And since we can always set, this part to 1 and this part to -1 without loss of generality, our problem is to find the correct values of these P1 and P2 components here. So here I'm plotting the values of the estimated P1 and P2 as a function of the noise strength. So for the generated data, we additionally added some random noise. And here we have added 20% noise and 25% noise. And as you can see, the estimate is pretty good. Up to a rather large noise level. And once we obtain this a combination, we can plot this data collapse plot, and this is the case where noise is 0, and as the noises increase and it gets worse, but the level of this data collapse seems not bad. But this is just test of the method. Using the artificially generated data, and what we want to do is apply this to some experimental data, and we have applied this method to the sure. Mm-hmm. Q is fixed. That's right.
The physical relation, it's even a priori, or even that combination can be actually anything. Right? For example, I can put also theta on the right hand side.
Theta?
Yeah. Theta, everything is dimensionless, so I can put theta also. Theta is 0 now. Okay, good. Then how do you know for the first time that relation? So, so in principle, probably you also have to change. Right?
So yeah, it's possible, and in the current problem we have fixed Q. Because in certain regime, we can consider certain limit, and we already know that this combination goes to a constant in this regime. So by considering some limit, we can find a certain combination. But it's also possible to estimate the multiple combination of the parameters. And regarding the sort of ambiguity in defining the combinations, it's true that the physical relation can be written in various ways. But the scale transformation symmetry is not affected by this choice because it is specified by this vector space. So as long as the individual choice of P and Q might change, but it doesn't affect. But this symmetry is determined by the choice of a vector space, and as long as the vector space is unchanged, we can find the the same scale transformation symmetry. So I mean, what I'm saying is that I mean, the apparent arbitrariness to describe the system, I mean, does not, I mean, affect the physical content of the scale transformation symmetry.
If I start with pi equals not a combination, pi equals something. So that means Q, my Q is just a 1, 0, 0, 0. If I just start with them, then I think your method also should work, right?
You mean that so you're going to consider some combination, like I mean,
And then in principle, you don't need that combination because you P will determine anything. So that in F, that there are 4 arguments. Theta.
function has one argument, but yeah, there's one combination. So this choice of this combination, I mean, corresponds to the choice of this P vector.
Yeah. So that was discovered by machine vector because
right.
You should
right.
The number of P you should is a machine learning result.
That's right. So
But
yeah.
Beginning, I don't know the combination. Machine does not know the combination.
That's right.
So it's the machine. There's a multiplication of the 4 parameters kappa, eta, theta, pi, right? And machine wants to determine only exponent.
That's right.
Right. So then, in principle, you can just start with that equation. Pi equals f and any combination.
So do you mean to start from, I mean, a function of multiple variables?
Theta to the P1, theta to the P2, kappa to the P3. That's my understanding. When you are doing right.
Yes.
And you discovered later that combination.
That's right. Yes.
Yeah, right. So does that also work instead of that equation? If you start with that equation.
So I mean, when performing the fitting, I mean, we haven't sort of we started from this one and perform optimization.
Yeah.
So this relation is, I mean, used to, I mean, generate the data.
Yes, that's right. Yeah. So then your machine will discover by using that formula, right? Arbitrary combination is okay.
Right. So yeah. So the machine was, I mean, able to find the right value of this, I mean, exponent. I mean, for yeah.
So machine does not know about the original formula.
The machine doesn't know anything about the, I mean, original equation motion or yeah. So it's, I mean, the method sort of works for this, I mean, generated data. I mean, and we have, I mean, applied this method to the data, I mean, taken by, I mean, this guy who is a co-author, and he has, I mean, created 127 points, which is not too many, and those are the estimated values of the parameters with some error bars. So if you look at these values, I mean, for example, this part, I mean, looks pretty close to -1/2, I mean, which corresponds to this particular model. And although the error bar is still large, I mean, the P1 is, I mean, 0.44, I mean, plus minus some error, which, I mean, seems a bit away from the 0, which is, I mean, predicted by the model. And if we plot, I mean, this, I mean, data collapse, it, I mean, looks like this. It doesn't look too bad, but it doesn't look too good. I do feel like we need, I mean, more data so that we can sort of narrow down the error bar and narrow down the error bar and pinpoint the scale transformation symmetry that exists in this system. But so this is at least I believe that it gives us some hint as to what is happening in these physical models. Because we once we find the self-similarity or the scale transformation symmetry, it sort of significantly narrows down the possible models to describe the system. And in that sense, I believe that this sort of method, I hope that this method is going to, sort of provide some useful, information for understanding what is happening in a complex physical phenomena. So that is basically what I want to say. So thank you for your attention.